Hi all. Today we will be discussing about the project face mask detector to detect whether a person is wearing a mask or not. So let us get into the details about the project. So mainly this project consists of two phases. First one is training the face mask detector, and the second phase is applying the face mask detector. The first phase consists of three parts mainly. So the first one is we will be loading the face mask data set. In the second part, we will be training the face mask classifier with Keras or TensorFlow. Then we will be serializing the face mask classifier to disk. So in the second phase, that is applying the face mask detector. The first part is to load the face mask detector, which we have already trained and placed in the disk. We will be loading that. Then we will be detecting the images from image or video stream. We will be extracting each phase ROI. ROI means region of interest of a phase. We will be extracting that. Then we will be applying the face mask classifier to each phase ROI to determine whether the person is wearing mask or without mask. Then we will be showing the results. So that's the main outline of the project. So we will be moving into the more detailed part about this. So as I have already told, the first phase is training and the second phase is deployment. In training, we will be focusing on loading our face mask detection data set from disk. We'll be training a model using Keras or TensorFlow on this data set, and then we will be serializing the face mask detector to disk. In deployment part, once the face mask detector is trained, we can move on to loading the face mask detector. We will be performing first the face detection, and we will be classifying each faces with mask or without mask by using the face mask classifier, which we have already trained and loaded. So so this is the data set which we are using in our project, that is with mask and without mask. So let us look into details about this data set. So actually the data set which we will be using here today was actually created by Prajna Bandri. So this data set actually consists of 1376 images belonging to two classes. First class is with mask, which consists of 690 images, and the second class is without mask, which consists of 686 images. So our goal here is to train a custom deep learning model to detect whether a person is wearing mask or without mask. So let us check how our face mask dataset was created. So to create this dataset, actually, Prajna had the ingenious solution of actually loading or taking the normal images of faces. Then we will be actually creating a custom computer vision Python script to add face masks to them, thereby creating an artificial dataset. So we can say that the dataset which we are using here in our project is actually not the real world pictures of people wearing masks. Instead, they had the pictures of real world faces with an additional mask applied on it by using a custom computer vision Python script. So actually, this is artificial dataset, but we can say it is still real world applicable. When I say about this creation of finding faces and then applying about this Python script, this method may seem more complicated, but actually this method is a lot easier than it sounds because we'll be applying the facial landmarks to the program. So this facial landmarks will allow us automatically to infer the location of facial structures, mainly like eyes, eyebrows, nose, chin, mouth, jawline, etc. So on finding the face landmarks, we are able to apply the face mask to our face easily, and we will be able to find the artificial data set very easily than it sounds. Okay, so let us check how it was created. So here, to use the facial landmarks to build a data set of faces wearing face masks, first we need an image of a person without wearing a face mask. So let us consider this image to be our example one. Then from there, actually we'll be applying the simple face detection technique to compute the bounding box location of the face in the image. So as shown in the figure, we will be computing the bounding box location by using the simple face detection program. Then Once we know where the face, where in the image the face is, we can extract the face ROI or the region of interest with OpenCV and NumPy slicing, like in the figure. And from here, we will be applying the facial landmarks, allowing us to localize the eyes, nose, mouth, etc. using DLib so that we know where to place the mask on the face. Actually, this project or this part of the project, like applying the facial landmarks and computing the eyes, nose, mouth, etc., is another simple and good, interesting project in OpenCV. So actually, I would suggest all of you to try using this simple project for the more detailed understanding of DLib, facial landmarks, OpenCV, all these things. First of all, I would like to suggest all of you to do face detection because the code is available. You will be able to understand it very easily. So try these projects on your own. You will get a better understanding of all the workings of OpenCV, deep learning, etc. So this is another interesting project in which you can all try on. So actually then we need an image of a mask with a transparent background such as the one below. Then this face mask will be overlaid on the original face ROA automatically since we know the face landmark locations. So this mask will be automatically applied to the face by using the facial landmarks, namely the points along the chin and nose to compute where the mask will be placed. So then the mask is placed on the image. Then this mask is resized and rotated, placing it on the face correctly. So we can then repeat this process for all our input images, thereby creating our artificial face mask dataset. So this looks somewhat original than we first took the assumption of doing an artificial dataset. So here another problem arises here is that if you use this set of images to create an artificial data set of people wearing masks, you cannot reuse the images without mask in your training set. So so we have to gather non-face mask images that we have not used in the artificial generation process of data set with mask. Actually, we need to include original images used to generate face mask samples as non-face mask samples. If we do that, our model will become more heavily biased and fail to generalize well. To avoid that by all costs, we need to gather some more time to gather new examples of faces without mask to make it more good detector. So in this project, actually, we will be reviewing about three Python script. First one is trainMaskDetector.py. So this one accepts our input data set, then fine tunes MobileNet V2 upon it, and we will be creating the mask detector model. This model is being loaded in the another two Python script to detect whether the person is wearing mask or not. So during this training process, there will be variation in the accuracy and loss. So we will be plotting a training history which contains the accuracy and loss curves. So that is also produced from the Python script named trainMaskDetector.py. Then we have detectMaskImage.py, which is used to perform face mask detection in static images. Then we have detectMaskVideo.py. So here we will be using our webcam, and this script applies face mask detection to every frame in the stream. We will be detecting whether the person is wearing mask or not. Then we have so this is the main Python script. So before we move on to the code explanation, I want you to be more familiar with the part of data augmentation. So what is data augmentation? So we can say that in simple words, it's a strategy which is used to increase the diversity of data available for training models without actually collecting new data. So that means if we have an image like shown in the figure, and we will be doing some data augmentation techniques such as cropping, padding, horizontal flipping, zooming, etc., to make the data set more efficient. So we'll be applying data augmentation on a single image. We'll be getting 5 to 6 images in different angles or positions, which will increase the diversity of our face mask data set. Actually, without collecting new data from a single image, we are trying to make more images. So this will increase the efficiency of our model. So now we will look into the code for each one of them. So let us look into the code. Actually, here we will be first, let me show you the project structure. Here we have, so this dataset folder, in this folder we have with mask and without mask images, which is given in another two folders. Then here in this examples I have loaded some images which will be used in the detect mask image.py to detect whether the person is wearing mask or not on running the Python script. Then we have the three Python script, train mask detector, detect mask video, detect mask image.py. Then we have the plot, which contains the accuracy and loss curves. Then we have the mask detector model, which is the model trained after our execution of train mask detector.py. So now we will look deeply into the train mask detector.py. So actually the train mask detector.py is to train a classifier to automatically detect whether a person is wearing mask or not. So let us look the code. You can see a large variety of imports shown here, right? So this imports for our training script may look odd to all of us because most of us are very new to do deep learning, TensorFlow, Keras, and each one of them. So actually, I would recommend all of you to read about Keras and fine-tuning tutorials after the session and then look into the code once again. So you will get a very better idea than the initial one. So our set of TensorFlow.Keras. So here we can see a lot of TensorFlow.Keras, right? So our set of TensorFlow.Keras imports allow us. First case, it is data augmentation. We know what is data augmentation, right? So to make the data set more wide, we are using data augmentation, and which is done with the help of TensorFlow.Keras. Then we are loading the MobileNet V2 classifier. So what is MobileNet V2? Actually, it's a very big topic, and I would like to shorten it and say it like it is a very highly efficient architecture that can be applied to embedded devices with limited computational capacity like Raspberry Pi and Google Corals. So that is the main advantage of MobileNet V2 classifier. Then here we will be tuning this model with pre-trained ImageNet weights. Actually, if you check for ImageNet weights, you will get another interesting topic to research upon ImageNet weights. Then we are using the TensorFlow.Keras for building a new full connected head. So what do you mean by a new full connected head? So first I would like to say about what is a convolutional neural network. Actually, convolutional neural network, or CNN, is a type of neural network that specializes in image recognition and computer vision tasks. So actually the CNNs have two main parts. That is, one is the convolutional pooling mechanism that breaks up the image into features and analyzes them. Then a fully connected layer that takes up the output of the convolutional pooling and predict the best label to describe the image. So a convolutional neural network leverages the fact that an image is composed of very smaller details or features and creates a mechanism for analyzing each feature in isolation, which informs a decision about the image as a whole. So that's what a convolutional neural network do. So as part of CNN, there is a fully connected layer that takes the end result of the convolution or pooling process and reaches a classification decision. So that's what the fully connected head is actually meant for. Then the TensorFlow Keras also allows us for pre-processing of the image as well as loading the image data. Then we can see here sklearn or scikit-learn library. It is used for binarizing class labels, segmenting our dataset, and also printing a classification report. Then we have imutils, right? iMudel's implementation will help us to find and list the image in our data set. So then we also have matplotlib, right? So this matplotlib is used here to plot out training curves of accuracy and the loss factors during the training section. Now we will be looking into the code. So check out here. So here we are using we are constructing the argument parser, which is actually giving the command line arguments. So let us look into each one of them. Here we have minus minus data set, which is the first one. So this minus minus data set is the path to the input data set of faces and faces with mask. Then we have minus minus plot. This is the path to our output training history plot, which will be generated using matplotlib, which contains the accuracy and loss curves. Then we have minus minus model, which is the path to the resulting serialized face mask classification model. So here I have also specified some hyperparameters. See, here we can see some hyperparameters. I hope you can see my cursor. So here we have specified some hyperparameters constants, including first one is initial learning rate, then number of training epochs and batch size. So with this part, we are now ready to load and pre-process our training data. So in this block, you can see in this block, actually we are ready to load and pre-process our training data. We are grabbing all of the image paths. Here you can see we are grabbing the image paths, right? Image paths from the dataset folder. I have already shown the dataset folder, which contains with mask and without mask two data folders, which contains the dataset which we have created. So here we are grabbing all the image paths in the dataset. Then we are initializing the data and labels list here. You can see here the data and labels list. Then here in this part, we are looping over the image paths. We are looping over the image paths in the data set, and we are loading and pre-processing the images. So here you can see the loading of the image, right? Here we are loading the image, then we are pre-processing the image. So what do you mean by pre-processing of an image? So pre-processing is mainly meant for resizing to resizing the image which we have loaded into 224 into 224 pixels, which is shown here. That is the arguments here. So we will be resizing it into 224 into 224 pixels, then conversion to array format, and then scaling the pixel intensities to the input image in the range -1 to 1 using the pre-processing input convenience function. That is the pre-processing input convenience function. Then we will be appending the pre-processed image and associated label to the data and label list, which is happening here. You can see that. Then we will be ensuring our training data is in numpy array format. So we converting the array, converting the list in numpy array format. Then now we will be encoding our labels, partitioning our data set, and prepare for data augmentation. So this portion is meant for one hot encode of our class labels. Then here we have, that is, this portion is for one hot encode. Then this portion is mainly for segmenting our data into about 75% for training and then testing 25%, so that partitioning is being happening here, which is using the scikit-learn convenience method. Then you can see we are creating an object for data augmentation, right? So during training, we will be applying on the fly mutation to our images with an effort to improve generalization. So we have already told about data augmentation. So this is known as data augmentation, where the random rotation, zoom, shear, shift, and flip parameters are established. So we'll be using this org object for the training time. Now actually we need to prepare MobileNet v2 for fine tuning. So fine tuning is done in a three-step process. First one is loading the MobileNet with pre-trained ImageNet weights leaving off head of network. So that is being done during this portion. Then we will be constructing a new fully connected head and append it to the base in the place of old head, which is happening here. So in this portion, then we will be freezing the base layer of the network, and the weights of these base layers will not be updated during the process of back propagation, whereas the head layer weights will be tuned. So that is happening in this portion. So here we will be looping over all the layers in the base models and freeze them. So they will not be updated during the first training process. Only the head layer weights will be tuned and updated. So then we will be doing so here we have our data prepared and the model.architecture in place for fine tuning. So we are now ready to compile and train our face mask detector model or network. So in this portion, we are actually compiling our model with Adam optimizer, a learning rate decay schedule, and a binary cross entropy. Then we have face mask training is launched. So here we can see how our data augmentation object we can see how our data augmentation object will be providing batches of mutated image data. So this will allow us to widen our data set, which contains only about 696 or 696 something for with mask and 686 something for without mask. So this will actually widen our data set and will make our data more efficient, our model more efficient. Then here we'll be making predictions. Here we'll be making predictions on the test set, grabbing the highest probability class label indices. Then we will be printing a classification report in the terminal for inspection. This portion serializes our face mask classification model to this. Now we will be plotting the accuracy and loss curves once our detection and classification report is completed. So here we will be actually saving this figure into this with minus minus plot file path. So into that image, we will be plotting all the curves using the matplotlib function or the library. Okay, so here we have completed our train mask detector.py. So actually we have now the main thing is to train our function, right? So we need to train the model by running the Python script. Actually this the command for the training is python train mask detector.py, python train mask train mask detector detector.py minus minus data set. So we need to load the data set for the function, right? So we need to, that is done using minus minus data set, which we have already done during the creation of our argument parser. And this is the folder which contains the data set images. So actually this is the code. I have already run this code and kept it because this will take a large amount of time for training, because almost 20 epochs is there. So that I have already completed that. So we will check on to the plot which contains the training accuracy and loss curves. So check out this. So here you can see the red line that almost points to 0 point something. So which shows the loss in this training is very less, right? So we can make sure that our face mask detector is very well accurate and efficient. And we can also see that the accuracy value almost points to 99, right? So which started from almost 0.8 something and which ended up in 0.99. So as we can see, we are obtaining about 99% accuracy of test cases. So we can tell that maybe our model is very good detector in face mask detection. So now we need to check out whether this model is correctly predicting or not. For that, first we need to look at the code for detect mask image.py, which is the Python script, which is used to check whether the person is wearing mask or not in a static image. So we will be looking on the code for that. Here also we can see some imports, which is used for the functions which we are using in this portion. Then we are So in this face mask detector, like we can say that detect mask image.py, there are mainly three things. First one is loading an input image from disk. Then we will be detecting face in the image using simple face detection. Then we will be applying our face mask detector to classify the faces with either mask or without mask. So we will be looking into the argument parser right now. So the first one, you can see the argument parser here, right? So the first one is minus minus image. So it is a path to the input image containing faces or inference. So this is the path from where we have to load the static image for testing during running this Python script in the terminal after explanation. So then we have minus minus face. So the path, it is the path to the face detector model directory. So that is for face detection, simple face detection. There is a file for, or a folder called face detection. Then we have minus minus model, which is the path to the face mask detector model that we have trained with trainmaskdetector.py. Then we have minus minus confidence. So it is an optional probability threshold that can be set to override 50% to filter out weak face detection. So actually we don't want to detect mask in a image where the face detection is almost less than 50%. We need not check out that. So to filter out that weak face detection, we are using a minus minus confidence. Then we have then we will be loading both our detector and face mask classifier models. Okay, so we will be now detecting, now we will be loading our detector and face mask classifier model, which is done in this part of our, so which is done during this part. So with our deep learning models now in memory, our next step is to load and pre-process an input image. We will be pre-processing an input image. For that we need to load an image, right? So upon loading our minus minus image, which is the path for input image for detection, we make a copy. We will be reading it, then we will be making a copy and grab frame dimensions for future scaling and display purposes. So pre-processing is handled actually by OpenCV's block from image function. As shown in the parameters, we will be resizing it to about 300 into 300 portion. Then we will be performing some mean subtraction on it. Here we will be actually detecting the face and localizing where the faces are, right? That is done during this part. Now we will be once we know where each phase is predicted, we will be making ensure that the minus minus confidence threshold before we extract the ROS, because if it is weakly detected phase, we need not find the phase ROI to act upon the phase mask detector model. So here we will be looping over, here we will be looping over our detection, and we will be extracting the confidence to measure against the minus minus confidence threshold. So here we will be finding the confidence of a detection. Then if the confidence is, that means we will be filtering out the weak detection by ensuring that the confidence is greater than the minimum confidence. So that is checked here. If confidence is greater than hours of confidence, then we will be computing the bounding box value for a particular phase and ensure that the box falls within the boundaries of image. So that is done here. This portion of the code ensures that thing. Then next we will be running the phase ROI through our masknet model. That is done here, right? So in this block actually we are extracting the phase ROI via numpy slicing. Then we will be pre-processing the ROI with the same way we did it during training. We will be pre-processing it like 224 into 224 pixel, all those things. Then image to array conversion. Then we will be finding the we will be doing the pre-process input using pre-process input convenience function. So what we have done already in the training part, we will be again doing that. Then we will be able to display the result with model.predict. So we will determine the class label based on probabilities returned from by the face mask detector model. So here actually we are trying to assign a color as well as a label for that. So here we have used red color for no mask and green color for mask. Then So we then draw a label. Then we draw the label text as well as a bounding box. That is done here. We will be displaying the label as well as the bounding box rectangle in the face using OpenCV rectangle drawing function, which is rectangle. So actually we will be drawing a bounding face to the face detector, and we will be showing a text or a label which shows the whether the person is wearing with mask or without mask. Then after once all the detection have been processed, we will be displaying the output image. So that is shown here. We will be showing the output image. So we need to check whether our system is working or not after explaining all these codes, right? So check out here. So this is the code Python detect mask image.py, which is the name of the Python file. Then minus minus image. We need to give the path for the image which we need to check. So that is given in the examples. Inside that we have example01.png. So we will be showing that. So this is being running. Yeah. See, you can see this was the image which have given us example01.png in the file folder. So you can see there is a green bounding box on the face detector, and there is a label stating the mask or without mask. Here it is with mask. So this is having almost an accuracy about 99%, right? 99.8% something. So this is the first image. So now let's check out an image without mask, right? So we need to check that also, whether it is being detected with mask or without mask. So let's check out another image. See, this person is not wearing a mask, so it is shown in red color with the label no mask, and it has an accuracy about 99.99%, right? So this is the image. Now, upon last, let us check another one image. This may cause a contradiction to our theoretical stating of things that it will show so and so, right? So here we have a complication, as you can see, isn't it? So actually what happened here, I would like to hear it from you guys, because this is actually really complicated one. So what happened here? Why is it we were able to detect the faces of the two gentlemen in the background correctly and stating that there is no mask for them, but we could not detect the woman in the foreground? Why is that so? So, always keep in mind that in order to classify whether or not a person is wearing a mask, we need to first perform face detection. If a face is not found, then the mask detector cannot be applied. So that's what happened here. The face of the woman in the foreground is not detected. That is, the confidence level for this particular face is less than 50%. So this is ignored. So the face mask detector model is not applied in case for the woman. That is why we were not given an output for the women. So the reason we cannot detect face in the foreground, it is because the face mask is too obscure. So this mask is actually covering almost more than 75% of the face of the woman in the foreground. So in that case, the face detection will be very less. So the face detector model is not applied here. And we also know that the dataset we have used here to train the face detector did not contain examples of image people wearing actual people wearing face mask. That means real world images were not present in our dataset. It was artificially generated. So that's also a problem in case of not detecting the face in the foreground. So we can say that if a large portion of the face is occluded, our face detector will likely fail to detect the face, and thus there will be no applying of face mask detector model. Now, implementing the face mask detector in real. So we will check out about how to solve this problem in the last section of a tutorial or webinar. And now we will be going to check out uh, the face mask detector in real-time video streams with OpenCV. So let us check that. For that, we need to open our detectmaskvideo.py. Let's open that and we will review the code in detail. Then we will be showing the output. Then we can discuss about how to solve the problem that is existing right now. So the algorithm for the script is the same, but it is pieced together in such a way to allow for processing every frame of your webcam stream. That's the only difference which we are facing from the one which we have discussed about. So that's the only difference. That's the only difference when it comes to imports. In that, we need a video stream class. So here we are importing one video stream class, that is IMUtils, uh, for time and video stream. So both of these will help us to work with the stream. We will also take advantages of IMUtils for this aspect aware resizing method. Then our face detection or mask prediction logic for the script is in the detect and predict mask function. So we can see we'll be dealing details about the detect and predict mask function. Here we have uh, this function detects faces and then applies a face mask classifier to each face ROA. Actually, the detect and predict mask function accept three parameters. You can see the frame, which is the frame from our stream. Then we have face net. This model is used to detect where in the image faces are. Then we have mask net. Our COVID-19 face mask classifier model is being passed here as masknet. So inside we construct a block, dictate faces and initialize list, two of which the function is returned. These lists include the faces, that is ROI, logs, the face locations, and threads, the list of mask or no mask predictions. So we have three lists here. One is faces, which contains the faces. Then we have logs, the face locations. Then we have threads, the list of mask or no mask predictions. Now from here, we will loop over the face detections. Inside the loop, we filter out weak face detectors and extract bounding boxes while ensuring bounding box coordinate do not fall outside the bounds of the image, as we have already discussed earlier. Right? We have already talked about this case earlier, that we will be finding the mask. I mean, we will be filtering out the least face detections. Then we will be checking whether the bounding box falls under the bounding box of the image itself. Then we will be adding phase ROIs to two of our corresponding list. Okay. After extracting phase ROIs and pre-processing, which is already explained, we append the phase ROIs and bounding boxes to the respective list. Now we are ready to run the phases through our mask prediction, right? So here we will be returning our phase, bounding box location, and corresponding mask or not predictions to the column. Here we will be returning all these details here. Then so our function is over. This is the main thing which we need to check out in this Python script. Then, as in the earlier cases, we have an argument parser which include three things. First one is minus minus face, which is the path to the face detector directory, minus minus model to the path to our face mask detector classifier, and minus minus confidence, the minimum probability threshold to filter weak face detections. So what is missing from the last one? We does not want an image, right? It is webcam stream, so we does not want an image. That's the thing lacking here when we compare it with the mask image py. Now with our imports, convenience function, and command line arguments, we are ready to go, right? So uh, we are just a few initializations to handle before we loop over frames. So here we are initialized for face detection. So this is the face detection model. Then we are loading the face mask detector and the webcam video stream. So we have initialized all three of them. Then will be proceeding to loop over frames in the stream. So we begin looping over the frames inside we grab a frame with the stream and resize it. So we will be resizing the frame which we have obtained from the webcam. From there we will then we will be putting our convenience utility to use, which detects and predicts whether people are wearing mask or not. So here we are calling our detect and predict mask, which we have explained just before. Then we will be looking at the post process of the mask detection, which is same as the last one. We will be keeping a color for mask and no mask, all those things. We will be putting a text, we will be drawing a bounding box, and then we will be showing the frame. So this thing will continue till we click Q. So we have given Q letter from the keyboard as the close or the queue function from the video stream. So when we click Q, our video stream will be off. Then we will be destroying all the windows. So I think the code is a bit familiar to all of you, because just a little changes of taking in a frame from the video stream, just resizing it all. That's all the difference here from the image, from when we consider with the image, right? So now we need to check whether our project is running with the real time video mask, right? So I want you to run the program using the script Python detect mask video.py, because we don't want to give any path to our image because it's direct from our webcam. So we will be checking out whether this is working. So guys, you can see my face right now, right? So I am not wearing a mask right now, and it shows there is no mask about 100%. They show that I'm not wearing mask for 100%. So let's try me wearing a mask right now. Okay. See, you can see now that the video stream shows that I'm wearing a mask for about 99% correct, right? So I think this project is somewhat good for you, in which you all can try this out during this COVID-19 situation. So let's click Q and Q from the webcam. So our project is almost over. So we have first we have trained a model, then we have checked out whether this works in static images, then we have gone to check whether this works in our webcam video stream, that means live stream, whether it is working or not. So now let us move back to our presentation. Yeah, okay. So here we have seen some issues, right? That the in the third image, the image in the foreground is not detected, but the image, two images from the background is detected correctly, and it shows that the persons are not wearing mask. So let's check out the suggestions for improvement in this session. As you can see from the results sections, our face mask detector is working quite well. Even though we have only very limiting data, the width mask class is being artificial generated. It is working quite well, right? So it's a good one. It's a good one, but we can improve our face mask detection model further. For that, we need to gather actual images of people wearing masks rather than artificially generated masks. Artificially generated images of people wearing masks. Then we need to also gather images that may confuse our classifier into thinking whether a person is wearing a mask or not, like which include shirts wrapped around faces, bandana over the mouth. So such images will actually confuse the classifier whether the person is wearing a mask. So we need to train our model with that too. Then finally, you should consider training a dedicated two-class object detector rather than our simple image classifier. Okay. So our current method, so we all know what is the current method of this project, right? First, we'll be performing face detection. Only if the face is detected properly, we will be applying our face mask detector to each face to check whether the person is wearing a mask or not. So the problem with this approach is that a face mask by definition obscure part of the face. So if enough of the face is obscured, the face cannot be detected, and therefore the face mask detector will not be applied, which happen in the third example of static images of detect mask image.py. So to circumvent that issue, we should always train a two-class object detector that consists of with mask class and without mask class, combining an image detector with a dedicated with mask class with will allow improvement of the model in two respects. So what's the first one? The first one is that the object detector will be able to naturally detect people wearing masks that otherwise would have been impossible for the face detector to detect due to too much of face being obscured. And the second one is that this approach reduces the computer vision pipeline into single step. Actually, in our thing, we have two steps. One is face detection, then applying the face mask uh, detector classifier, right? So if we change our project to in this way, this approach reduces the computer vision pipeline to a single step. So that's the main advantages of or the suggestions for improvement in this project. So I think this project will help you to understand a bit more about computer vision, deep learning, etc. So thank you. I would also suggest you reading about more details about all these things. And if you have any doubt, I would like you to contact me at andriaaj17@gmail.com, which is being shown in this notepad. I think you can see that. So if you have any doubts on this, or if you need any more clarification on any of the topics which I have covered today, you can always ping me at andriaaj17@gmail.com. Okay. So thank you, all of you, for this webinar, for attending this webinar or seeing this video. Thank you.